it wants us to calculate the reactance of this circuit. So for that, we're going to want X equals simply XC. There's no inductor, so there won't be any inductive reactance, just capacitive reactance. And the formula for that, if you recall, was 1 over 2 pi FC. So we would get this. I get 4 ohms out of that. And so the capacitor is going to contribute 4 ohms. And the resistor is also 4 ohms. So we'll each contribute 4 ohms at this particular frequency. Now, it wants a diagram showing resistance, reactance, and impedance for this RC circuit. So we can draw them as vectors in a complex number plane. And the way that looks is the horizontal is going to be the real component of the resistance. And then there's going to be a vertical component, which is the imaginary reactance contribution to the circuit's impedance. So what we do typically for these is draw the resistance pointing to the right, and then we have to decide, is our reactance going to be up or pointed down? We would now want to draw the capacitive reactance. And so I would draw that pointing down. So that would be our what's called XC in the complex plane. And so you can write them like this, that R is a real 4 ohms, but the XC is negative 4 ohms J. And it's supposed to stand for an imaginary number in this context. Even though we usually use I in math, they don't use that in electronics because I stands for current, electron current usually. Anyways, that is our setup. And now we want to draw one more vector, which is the impedance vector. And we've seen before how impedance is a sum of reactance and resistance. We even have this formula for it, that Z magnitude will be the square root of the squares of R squared plus X squared. And that's a picture of the impedance Z. So that's the diagram that it's looking for there. There's another interesting diagram though that we like to draw as well, and that is a diagram for the voltages. So when it comes to the voltages, you can have them just follow their individual associated components. And so we would have a vector pointing this way, which would represent the voltage in the resistor. And you can draw a vector pointing this way, showing the voltage in the capacitor, called VC, and then we'll do one more. But what goes here is the voltage associated with the impedance. Now the impedance is the overall constriction on current in the AC circuit, and that determines, well, it determines the current, but the voltage of the source is what's used to find that current. So we want Vs pointing this way. It says find the magnitude of impedance. Let's find it. Z equals the square root of 4 ohms squared plus 4 ohms squared. It's going to be 4 radical 2 ohms, which is about 5.66 ohms. It wants us to find the phase difference between VR and VS. So that can come from the diagram that we drew. It wants us to find this angle right here. That angle there is going to be the same as this angle here. And we can use the numbers associated with these vectors to find it. So we'll do tan inverse of 4 ohms over 4 ohms. Oh, that's 45 degrees. So when we go to plot our voltages for the different components, we're going to see sine waves. And we want the sine waves to be shifted so that they're not in phase. Now we saw in the past, like just to bring up some simpler examples, that if we just had a source and a capacitor alone, in that case what you would get as a graph when you're looking at the voltage, you could draw the source and you could draw the voltage of the source and the voltage of the capacitor. It's supposed to be that they would be in phase with each other according to Kirchhoff's loop law. So if the voltage of the source had been 10 volts at the time that we're drawing, then the capacitor would have to have 10 volts across it at that time as well. So what you would see is you'd see two identical sine waves where the voltage of the source just goes along with the voltage of the capacitor. But we also said that the current would not be in phase with the capacitor voltage. We said that current had to lead capacitor voltage. And so in this case, current should look like this. And so if you draw them on the same axis, you may see something like this. And that is the current. Notice that this one hits its peak 90 degrees before the voltages did. That way it fills up the capacitor while it's flowing forward, and it stops, the current stops when the capacitor is fully charged. And so what's going to happen here is it's a little more complicated, because now you have a resistor involved as well. If I was drawing the phasor diagrams for this, we would just see that you'd have a voltage of your capacitor would point down. So you got your voltage of your capacitor and you got your voltage of your source. They're in phase because the capacitor is the only thing contributing to this. And then of course they would just rotate around like this together. But what we have here is the resistor voltage is pointed at a different angle than the capacitor voltage. They're 90 degrees apart. And so the source will now have to be, it'll have to be taking both of them into account, is the idea. Alright, so we want to find the maximum voltage that the source, the resistor, the capacitor all individually reach. So there's formulas for that. For the voltage of the source, this guy is going to go along with this guy according to the mathematics we've used so far. So we will have Vs max will equal I max times Z. Alright, that's the formula we've used. So we know what the Z is. It's right here. And we also are given the source voltage earlier in the problem. It says use a max voltage of 12 volts. So this is something we can plug into. 12 volts equals I max times 5.66 ohms. And we can solve for what the I max is. And knowing that max current is really critical to drawing the rest of this. It's 2.12 amps. So I'm going to write that just here, that I max is 2.12 amps. Now, to create my function for Vs, I simply need to start with Vs max, and then I can use sine of some angular speed, angular frequency, times t. But I want to shift that guy a little bit, and here's why. The voltage of the source in my picture is not on the zero. You know who's on the zero is the voltage of the resistor, so I would rather put him as Vr max sine of omega t with no phase shift, because it is pointed at 0 degrees in my picture. But when it comes to the source, that one is shifted. And it's shifted by subtracting the phase angle there of 45 degrees. Okay, so that's how we shift these sine waves according to the phasor diagram. Now over here with the capacitor, we'll do Vc max sine of omega t minus 90 degrees. Or you could put pi over 2 if you're doing radians, either one. And so that's what we want to do. We just want to edit these. I know what Vs max needs to be. According to the givens in the problem, it needs to be 12 volts. So we'll just put that in. It's a little bit tougher to find the max voltage of the resistor and the max voltage of the capacitor, but I do also know the phase angle is going to be 45 degrees for the source. Now let's find Vc max and Vr max. We actually would use the current of the overall circuit as part of our calculation and finding those. We just have to write that Vc max will be I max times Xc. It's based on the reactance of the capacitor. And Vr max, of course, is going to be based on the resistance. So let's plug in here. Let's see, we're going to get Vc max equals 2.12 amps times 4 ohms. Vr max equals 2.12 amps times 4 ohms. I get 8.48 volts. So, alright, let's put in our values that we found. 8.48 volts and 8.48 volts. The last thing to do is to just figure out what the omega is for this circuit. We always have that omega can be 2 pi f. So that's going to be 2 pi times 60 hertz, which is 120 pi radians per second. So what I'm going to do is I'm going to plug that value in. I'm also going to change my angles to radians. Alright, and that should do it. When it comes to the current, we want the max current that we found, 2.12 amps. And this guy will be in phase with the resistor voltage, according to what we had looked at previously. Just plot them in Desmos and see what they look like. Okay, we're going to have to really rescale so that we can see better. I'm going to zoom way in on the time axis. Okay, let's change this to, say, 15 volts, negative 15 volts. Alright, so there's our capacitor voltage. Capacitor voltage follows current. This is correct. Yeah, because the capacitor voltage is 90 degrees behind. You can see it in the phasor. It's 90 degrees behind the resistor.